Okay, does anyone have any questions they'd like to ask? Okay. Don't all talk at once now. You need to take your turn. Okay, since there aren't any questions, let's take a look at some problems, okay? Well, we have one more entering. Maybe that person will have a question. All right, Gabe, can you hear me?
I can hear you.
Okay, we're recording. Do you have any questions you'd like to ask at the beginning of class?
I'm not at the moment, no.
Okay, that's fine. We're going to go ahead and do some problems then. I'm going to change my share and here we go. Okay, so y'all can see this problem. And when I say y'all, that's from that 3 months I lived in Alabama. Or maybe it was that year I lived in Texas. I don't know. Okay, so we're going to go do some problems from the back of the book. I've picked a select few that we should have time for. So Alka-Seltzer contains 324 milligrams of aspirin. Blah, 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 blah. The last two compounds, blah, blah, blah. Calculate the moles of each substance in the tablet. Now, I'm going to focus on aspirin and not the rest because there's a follow-up question about aspirin. So we're going to calculate the moles of aspirin. You do the same thing for the other substances. So let's look at aspirin. Can everyone see what I'm writing?
Yes.
Okay, excellent. So aspirin is C9H8O4. So first thing we need to do is we need to figure out the molar mass of aspirin. Now there's 9 carbons, and they each weigh 12.00 or 12.01 grams. So that comes out to 108.09 grams. There's 8 hydrogens, each weighing 1.01 grams, which comes out to 8.08 grams. And there's 4 oxygens, each weighing 16.00, which comes out to 64.00 grams. We add these all up together and we get 17 here. We get 0 here, carry the 2, and we get 180.17. So this means that 1 mole of aspirin, and I'm going to abbreviate it at ASP, is equal to 180.17 grams, or we could say 1 aspirin itself equals 180.17 U. It means the same thing. Are there any questions about getting the molar mass of a substance? Okay, there being none, let's calculate the moles of aspirin in our tablet. So I'm just going to say that since they tell us how many grams of aspirin are in there, 324 grams of aspirin, and that's milligrams, my apologies. We want to turn that into grams and then turn that into moles. So one way to do that, I'm going to move my sheet of paper up, is to take 324 milligrams of aspirin and multiply by 1,000 milligrams of aspirin per 1 gram of aspirin, and then multiply by, and the milligrams cancel. And then I'm going to use this conversion right here, and I'm going to put 180.17 grams on the bottom. And I'm going to put 1 mole of aspirin on top. So this is one way to do it. If you look at this answer here, you can see 180 goes into 324, not quite 2 times, but almost. So you know the answer here's got to be like a 2 point something, and then this becomes 10 to the minus 3. We get 3 significant figures because of the 324. And so I get 1.80 times 10 to the minus 3 mole of aspirin. Now, another way to do it would have been this: 324 milligrams of aspirin is equal to 324 times 10 to the minus 3 grams of aspirin. And then times 1 mole of aspirin per 180.17 grams of aspirin. So as you're writing this one out, you'll notice that I simply took that M and substituted 10 to the minus 3 for it, because that's what M means. The answer is going to be the same: 1.8 times 10 to the minus 3 moles of aspirin. So, if you showed me that on the test, that would be fine. If you showed me that on the test, that would be fine. And if I asked for the molar mass and you showed me this on the test, that would be fine. Notice I don't have any units here, but it's understood. We're calculating either the grams or the atomic mass units, depending on whether we're talking about a mole or one. Are there any questions about this? Okay, let's look at the second part. If you take one tablet, how many molecules of aspirin are you consuming? So for the second part, we need to know that 1 mole of aspirin is equal to 6.022 times 10 to the 23 aspirin, or aspirin molecules if we want to write that out. So we can take this value here and multiply by this conversion factor. You can see we're going to get a really large number, basically 10 times 10 to the 20, something like that. Or 10 times 10 to the 20 would be 1 times 10 to the 21, somewhere in that range. So I get 1.08 times 10 to the 21 aspirin. So, this is the kind of work I'd expect to see for the second part. Now, is that a lot of aspirin or not? I don't know. I'm going to do a little quick search here on the internet. And what I'm searching for is the number of cells in a person. And 37.2 trillion comes up from nationalgeographic.com. Sounds like a huge number, right? 37.2 trillion. So we have 1.08 times 10 to the 21 aspirin molecules being used by 37.2 trillion. So that would be million, that would be billion, and that would be trillion cells. So let's find out how many molecules each cell gets when you take a tablet that has 324 milligrams of aspirin. Okay. 37 to 1, 2, 1, 2, 3, 1, 2, 3. Oh gosh, I lost track. 2, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so that comes out to 2.9 times 10 to the 7 molecules per cell, and that number is 29 million aspirin molecules per cell. 29 million. So maybe that's why they recommend those little baby aspirins instead of some big old honking aspirin like this. This is 1/4 of that. So that means that you wouldn't be getting 30 million per cell. You'd only be getting like 7 million per cell. Okay, so does it sound like a lot?
Yeah.
What do you think? That sounds like a lot, doesn't it? One aspirin, 80 milligrams, is 7 million aspirin molecules per cell. What does that tell you about the size of aspirin molecules? That there's not 7 million per cell, but there's 1.8 times 10 to the 21 aspirin molecules on one little tablet. I mean, aspirin molecules are so small that you don't say they're teeny, teeny. You don't say they're teeny, teeny. You don't say they're teeny, teeny. You just say they're so small you can't see them. Okay. Any questions about that? Okay, so you know what kind of work I would expect to see for that problem. Let's move on. We're going to be learning some new material today that we haven't covered before. So this says calculate the mass percent of titanium in the mineral ilmenite. And here's the formula for ilmenite. What mass of ilmenite in grams is required if you wish to obtain 750 grams of titanium? So here, this gives me the advantage of showing you how to calculate mass percent and how to use percent. So mass percent, we'll say of X in Y is equal to the mass of X over the mass of Y times 100%. So in this particular case, the mass percent titanium in ilmenite would be the mass of titanium over the mass of ilmenite, which is FeTiO3, and then times 100%. That looks like Mars. Now it looks like mass. So in this case, how do we get the mass of titanium? Well, we could use either the mass of one titanium atom, or we could use the mass of a mole of titanium. So in our book, titanium to 4 significant figures, or to the 100th, I should say, is 47.87. And I'm going to put U here. And the mass of this is going to be 55.85 U plus 47.87 U plus 3 times 16.00 U. And all of that times 100%. So you can see all the units cancel out. And let's see what we get for our answer. So I've got 47 point, well, let's estimate the answer. 3 times 16 is 48. 48 plus 47 plus 55 is about 150. So this is about 50 out of 150. So roughly the answer should be 1/3 or 33%. And this morning, I think we got 31.55%. So let's double check. Well, clearly I did something wrong because I got a number of less than 1.
Yeah.
Okay, I do get 31.55%. It's 4 significant figures. And the reason for that is if we take a look at the 55.85 and the 47.87 and this, which is 48.00 with 4 significant figures because the 3 is exact and this has 4 zig figs. You add these all up together and you get 2 carry the 1. And then you get 9. Oh, my bad. You get 7 carry the 1. Then you get 1 carry the 2. And then you get what looks like 15. Okay, so here, this is good for 5 significant figures. So 4 zig figs divided by 5 zig figs times infinite, because percentage is exact. You get 31.55%. Any questions there? Okay, there being none, I want to show you what this means. This means that you have 31.55 grams of titanium in 100 grams of this ilmenite. So that's what this means. Is everyone okay with that? How do I know it means 31.55 and 100 grams? And the answer is because percentage means 100% exactly, not kind of, not sort of, exactly. It's defined. Okay, so now I want to take my 750 grams of this ilmenite and I want to figure out how many grams of titanium I have. So I'm going to take the 750 grams of ilmenite and I'm going to use this idea down below. So what's going to go on the bottom? The 100 grams of this iron, titanium, or the ilmenite. And what's going to go on top is the 31.55 grams of titanium. Oh, my bad. We got to cross this whole thing out because it doesn't ask if you start with 750 grams of titanium or ilmenite. It says you want 750 grams of titanium. So how much ilmenite do you start with? So how am I going to use this when we want that? So we want that. I'm going to take the 31.55 grams of titanium and put it on the bottom. And I'm going to put the 100 grams of the ilmenite on top so that we can clearly see that the titanium cancels and we're left with the ilmenite. And we know that this answer should be basically, this will go into 100 about 3 times. So 3 times 750 makes it about 2,250. So I get, I don't get 2,250, but I get 2.4 times 10 to the 3rd grams. Now, why are there only 2 significant figures here? And it's because of the 750. Are there any questions there about why there's only 2 significant figures here? So this is the kind of work I would expect to see for the second part. And this is the kind of work I would expect to see for the first part. So let me move that over so you can see the whole answer in its totality. Are we good to go? That's a yes or no.
Yes.
Yeah.
You can always give me the thumbs up too. Okay, we're going to go to this next problem. An organic compound has the empirical formula of C2H4NO. If its molar mass is 116 grams per mole, what is the molecular formula of the compound? So you need to know the difference between an empirical formula and molecular formula. So molecular formula, I'm just going to call MF, and that is the ratio of atoms. There's something called hydrogen peroxide, and the molecular formula is H2O2. That means in this particular compound, there are exactly 2 hydrogen atoms. There are exactly 2 oxygen atoms, and that's the molecular formula. Now, if we look at the empirical formula, it's the simplest ratio. So this same molecule for the empirical formula, it's HO. Now, another example, the molecular formula for water is H2O. The empirical formula is H2O. So sometimes the molecular formula and empirical formula match. Now, how do you get the molecular formula of a problem if you know the empirical formula and you know the molar mass? So notice, we're given the empirical formula and we're given the molar mass. Well, to calculate the molecular formula, you're going to take the empirical formula and use a multiplier. So how do you get the multiplier? The multiplier is equal to the molar mass of the molecular formula divided by the molar mass of the empirical formula. So MM is molar mass. So the molar mass of the molecular formula is given right here. Now, what is the molar mass of the empirical formula? Well, we've got 2 carbons, 4 hydrogens, 1 nitrogen, and 1 oxygen. So for the carbons, we've got 2 times 24. Well, for the carbons, we've got 2 times 12.01. For the hydrogens, we've got 4 times 1.01. For the nitrogen, we've got 1 times 14.01. For the oxygen, we've got 1 times 16.00. So when we add these all up together, we get 07, 30, 34, 58. So I'm going to divide by 58.07 grams per mole. And I'm not going to worry too much about whether or not this goes into this twice or 3 times or whatever. It's obvious it goes in 2 times, but not quite, maybe 1.999. I'm not going to worry about it. It's 2. Whenever you get this multiplier, it should always be close to a whole number. If you get a multiplier like 1.2 or 1.4, you messed up somehow or other. Okay. If you get a multiplier like 1.1, it may be that your data is a little off. Okay, so here we're going to say the molecular formula is going to be C2H4NO. And remember, that's given above. And then we're going to put a 2 here. That's the multiplier. And so the molecular formula is C4H8N2O2. So this is the kind of work I would expect to see for a problem like this. Are there any questions about this, or are we good to go? Are we good to go? That's the question.
I'm curious when it comes to the molecular formula, you use the hydrogen peroxide as an example. So if it was the EF of hydrogen peroxide, it would just be HO. Is that correct?
Empirical formula.
Okay.
Empirical means found by experimentation. And by experimentation, you wouldn't actually find that it's 2 to 2. You'd find that the ratio is 1 to 1. When you do these experiments, you find the ratio, not how many.
I'm sorry, I got confused. I thought you were going across and you went down from the
Right
MF
there.
to the EF. Yeah, okay. Never mind.
So EF is empirical formula. Okay, so let's put that one off to the side and let's take a look at the next problem. So this is just to kind of solidify what we just learned. So if we take a look at A, we know the molar mass is 150. We know the empirical formula is C2H3O5. So the molecular formula should be the empirical formula with some multiplier. And we know that multiplier is equal to the molar mass of the molecular formula divided by the molar mass of the empirical formula. So in this particular case, they give us the molar mass of the molecular formula here. And here, if we look at 2 carbons, 3 hydrogens, and 3 oxygens, we don't even need to do a good job here. We know each carbon weighs 12, that's 24. Each hydrogen weighs 1, that's 3. Each oxygen weighs 16, that's 48. Add that up very quickly and you can see that we've got what, 75, right? So here, 150 divided by 75 grams per mole gives you what? 2. So that means that the C2H3O3 2 becomes C4H6O6. That's A. So here's B. I'd like you to do B and then let me know when you're done. Give me a little thumbs up that you're done. Or a yes, or whatever symbol you put in that participant list, I'm going to assume you're done. Okay, we got one person who's done, or they've given up, one or the other. Yeah, I'm just saying when you're done, and done means you're done like I'm done. Or it could be I'm done. Or it could be like I'm so done. Okay, we're given this number here. What is the molar mass of 3 carbons? 36. What's 36 plus 8? 44. What's the multiplier? 1. So that means the molecular formula is the empirical formula with the multiplier of 1, which means C3H8. So it turns out the molecular formula is the same as the empirical formula, just like my example with H2O, where the molecular formula and the empirical formula are identical. Okay, how about B? What is the empirical formula here?
You mean C?
Oh, C. So what's the answer for C? Well, remember, the empirical formula is the simplest ratio. This is B4H10. How can that be simplified? B2,
B2H5.
that's the empirical. Now, what's the molar mass of the molecular formula? Each boron is 10.81. Each hydrogen, of which there are 10, is 1.01. So this is 10.10. This is 4 times 0.81 is what? 3.64. And then you have another 40 added on to that. So I believe you get 53.74. And that would be grams per mole. We don't need to write that into the answer because it's right there at the top of the table. Any questions about that one, people? Or are we good? Are we good to go? Okay, we got one good to go. Rest, you still good to go? Okay, we're good to go. Okay, so this next one, we're asked to determine the empirical formula and molecular formula of nicotine. So nicotine, a poisonous compound found in tobacco leaves. It's not funny, it is poisonous. Are any of you smokers? Because if you are, you should stop. It's not good for you.
Just in case you haven't heard.
You got to even put a little label on the package. It says, I think it says, this stuff will kill you. And if it doesn't say it in those words, it should say it that way. This stuff will kill you.
Slowly.
Well, some people, it happens pretty quickly. Okay.
Well, true when everything accumulates.
So the empirical formula, here are the steps. When you're given the percentage, you take the percentages and turn them into grams and turn them into moles. And then you use the moles to get the formula. So those are the steps. Take your percentage, turn them into grams, turn the grams into moles, and use your formula. So here's the first step. We're going to say we have 74.0 grams of carbon. And we're going to say that we have 8.65 grams of hydrogen. And we're going to say we have 17.35 grams of nitrogen. And this would be the case if we had 100 grams of nicotine, because this 74.0 means 74.0 grams of carbon for 100 grams of nicotine. That's what the 74.0 means. It does not mean 0.74. It means 74.0 grams out of 100 grams exactly. And 8.65 grams of hydrogen out of 100 grams of nicotine exactly. You know, too bad nicotine is bad for you, because that actually sounds like a kind of cool name, right? What are you going to name your child? Oh, I'm going to name it Nicotine. Or if you want, it could be like a Nicotine, like an Italian type name. And then their nickname would be Nico. Oh, it's too bad nicotine's a bad stuff. 17.3.
Well, Nico is an Italian name.
Yeah, well, it's a short actually for a longer name, isn't it?
Probably. I know a Nico baby, actually. Italian child.
And I believe there's a famous singer, not a famous, maybe infamous singer from like the 70s named Nico. She also, I think, worked with the Velvet Underground for a little while. Okay, so that's what each of these numbers means. And so what we're doing here when we say turn the grams into moles is we're assuming we have 100 grams of nicotine. That's our assumption, 100 grams of nicotine. 74 of those grams are carbon, 8.65 grams are hydrogen, and 17.35 grams are nitrogen. Now I'm going to multiply by 1 mole of carbon per 12.01 grams of carbon, and we're going to get the moles of carbon in here. So I get 74 divided by 12.01, and I get 6.162 mole of carbon. And here I'm going to do 1 mole of hydrogen per 1.008 grams of hydrogen. And I'm going to use 4 zig figs here. Actually, I'm going to use 1.01. So 8.65 divided by 1.01 better come out close to 8.65. Agreed? And it comes out to 8.56. And then our 17.35 grams of nitrogen times 1 mole of nitrogen per 14.01 grams of nitrogen comes out to be 1.238 mole of nitrogen. So what do you do with these numbers? I'm going to show you how I deal with it. It's the easiest way for me to think about it. This means that I've got carbon 6.162, hydrogen 8.56, and nitrogen 1.238. That's the ratio, because formulas show the ratio of atoms. However, the formulas show the simplest ratio of atoms, and we don't get to have fractions. So how do we get rid of all these fractions? And how do we make sure that none of these numbers is less than 1? Because you can't have less than 1 atom. And the answer is I take this and I divide by the smallest. So when I divide by the smallest, I am keeping the same ratio, but I'm getting a different set of numbers. Now, I think we can all see that this last number is 1. Let's see what these other numbers end up being. So 6.162 divided by 1.238, and I get 4.977. Hydrogen, I get 8.56 divided by 1.238, and I get 6.91, and I get nitrogen 1. Now here, the only question that remains is, do I think these are close enough to call it good and call it C5H7N1? And there's a way to test it. So let's say that that is the empirical formula, because I'm rounding these. These are pretty close to whole numbers, agreed? And you can't expect your experimental data to be perfect, because this is supposed to be experimental data. So let me show you a good way to find out whether or not this is or is not correct. Okay? So let's go to the molecular formula. Remember, we're going to get our multiplier, which is the molar mass of the molecular formula divided by the molar mass of the empirical formula. And I want to remind you that we were given the molar mass of the molecular formula is 162 grams per mole. Now, if this turns out to be pretty good, then chances are it'll add up to 81 because 81 will go into there 2 times. So let's see, 5 times 12 is 60. 1 times 7 is 7. And 1 times 14 is 14. And that adds up to, lo and behold, 81. So our multiplier is 2. And the molecular formula is going to equal C5H7N doubled, which is C10, H14, N2. So I'm pretty confident that this is the empirical formula because it is precisely half the molar mass of the molecular half the mass of the molar mass. So when you're ready to move on, give me a little thumbs up. And if you have any questions, for goodness sakes, please ask. And if for goodness sakes doesn't do it, then for badness sake, do it. So what kind of work would I expect to see out of this one? I'd expect to see this. I'd expect to see this. And all the way down to here. I don't expect to see that. And I would expect to see this. Any questions, people? Are we good to go?
I've got a question. How long do we have to take our test? Your speed
100
is amazing, but I'm
150
scared.
minutes,
For how many questions?
11. So you can see I did this problem in what amounts to probably 5 minutes, right?
Yeah.
And you should be able to do it in 15.
Well, that's a little more relieving. Thank you.
And in my 5 minutes of doing it, I'm actually writing it out. I'm not just telling it to you. I can tell you how to do it in 1 minute. I can tell you how to do it in 10 seconds. You ready?
No.
Take the percentage. Take the percentage,
yeah.
assume they're grams, take the grams, convert them into moles, and then use the moles to find the ratios to get the formula. Boom. That's how you do
Yeah,
it.
I got that down and I already highlighted that. It's just being able to retain that on the test. I'm, just
Well,
a little worried.
I tell you what, if you do 2 or 3 of these problems without looking at the book, then you've got it. Okay,
Hopefully so.
let's take a look at this one here. Elemental sulfur is combined with fluorine to give a compound with the formula SFX, a very stable colorless gas. You have isolated 5.722 grams of this SFX, which almost sounds like a cable station. What is the value of X? So you have sulfur, which we know is a solid because we know that the only 2 liquids at room temp are mercury and bromine. And we know that this isn't a gas because it's not one of the 12 gases. Reacts with F2, and we know that this is one of the gases. And you get SFX. And we know that this is a gas because it states so. Now, this is not supposed to be a balanced chemical reaction. I'm not worried about that. And the reason I'm saying that is because I know you've taken chemistry before, so you know about balancing reactions. Well, if we don't know X, we can't really balance the reaction right now. Okay, we start off with 1.256 grams of this sulfur, and we end up with 5.722 grams of SFX. So my question here is, how many grams of fluorine are there? And remember, the mass that we start with has to equal the mass that we end with. So that means that the mass of fluorine plus the mass of sulfur has to equal the mass of this SFX. So that means that the mass of fluorine is going to equal the mass of SFX minus the mass of sulfur, which is 5.722 grams minus 1.256 grams. And so that would be, I don't know, 12 minus 6 is 6, 11 minus 5 is 6, 6 minus 2 is 4, and 5 minus 1 is 4. So 4.466 grams. Okay. Now we want to find out the formula of this guy. And if you remember, we were able to figure out the formula of something using percentages, right? But we don't have the percentages here. But we could figure out the percentages, couldn't we? What is the percent sulfur in this compound? Well, we know there's 1.256 grams of sulfur, and there's 5.722 grams total. And we could find out that there's a 1.25, I'll turn this on. So there's a 21.95% sulfur in this compound, which of course then means that for the fluorine, there's a 78.05%. Because to get this number, I simply subtracted that from 100. So we could take these percentages and do what we just learned how to do, correct?
Mm-hmm.
Where we take percentage, turn it into grams, but we're not going to do that because it's a waste of time. What we're actually going to do is I'm going to take the 1.256 grams of sulfur and turn that into moles. So here I get 0.03916 mole of sulfur. Any questions there?
Oh.
Okay. Now we have this right here, 4.466 grams of fluorine. And notice this says F2 and I'm doing F. So let's do this. And we'll do it with F2 also. So for F2, I know that there's 1 mole of F2 per 38.00 grams of F2. And I know there's 2 mole of fluorine per 1 mole of F2. And I get 0.2351 mole of fluorine. Let's do the same for the above. We're going to do 1 mole of fluorine per 19.00 grams of fluorine. So notice here, if I start with F2, I got to use the molar mass of F2. If I start with fluorine, I got to use the molar mass of fluorine. When I put this into my calculator, I get 0.2351 mole of fluorine. So what point am I trying to make here? Doesn't matter whether you assume that you have diatomic fluorine or whether you have monatomic fluorine, you have 4.466 grams, period. So which way is easier? Starting with just the monatomic fluorine or doing the di? I think the monatomic. So now I'm going to take the next step which would be to say, I've got sulfur 0.03916 and fluorine 0.2351. Which number do we divide by? The smaller or the larger? Smaller.
Smaller.
So I get sulfur 1 and fluorine, what is X? Now, I don't really like this problem because I think they either screwed up and gave us the wrong numbers, or they're talking about a compound that is really wild. Oh, I guess I did my calculation wrong this morning. So I get 6.0023. So what is the answer? SF6. Any questions about that one? So to kind of wrap it up, we saw that we could take percentages, turn that into grams, turn that into moles, and turn that into the formula. But if we're not getting percentages, we can go ahead and take the grams, turn that into moles, and turn that into the formula. This way is actually shorter than that way. We don't make any assumptions. We just say, oh, there's how many grams. How do you think we do this experimentally? We do it this way. Okay. Are we good to go?
Yes. We're good.
Okay. We got one yes, we got 3 yeses. Excellent. So let's go to this next one, not that one, this one. This one, nothing really for us to learn other than the term allotrope. So allotrope are 2 different forms of the same element. For instance, carbon has a number of different allotropes. One of them is diamond. You guys have always heard that diamond is made out of pure carbon, but you've also heard that graphite is made out of pure carbon. And these are 2 different forms of diamond. There are other elements that are like this. You consider oxygen, there's O2 and there's ozone. Phosphorus, there's white phosphorus and there's red phosphorus. So these are different physical manifestations, if you will, of each element. And they have their own chemical behavior. They behave differently. Okay, so that's what I want you to know about allotrope. Allotropes are like isotopes, but they are different physical forms of an element. Capiche? So, which one should you know? None of them. I mean, you should probably know diamond and graphite, right? Okay, now, the recommended daily allowance for iron for women 19 to 30 years old is 18 milligrams. How many moles of this? How many atoms? So we're going to take our 18 milligrams of iron and turn that into grams and then turn that into moles. So the way I would do this is I'd start off with 18 times 10 to the minus 3 grams of iron right away. And I wouldn't monkey with trying to convert that. And one of the reasons I wouldn't try to convert that is because I may make a mistake. Here, I know M means 10 to the minus 3. Boom. That's a guarantee. Now, for iron, we've got 1 mole of iron per 55.85 grams of iron. So that'll give you how many moles we have. And let's see, 18 second EE negative 3 divided by 55.85 is equal to 3.2 times 10 to the minus 4 mole of iron. So this is less than 1 mole of iron. Can you have less than a mole of iron? Yeah. It's kind of like asking, can you have less than 1 dozen eggs? Yeah. Okay, how many atoms? We would take our 3.2 times 10 to the minus 4 mole of iron and multiply by 6.022 times 10 to the 23rd irons per 1 mole of iron. And the more I say iron, the more I think I'm not saying it correctly. It's one of those words, you know what I'm talking about? Where you say it over and over again and you're like, who the heck came up with that one? So 1.9 times 10 to the 20 irons. I don't know. Sometimes I tell you what I'm thinking, and I probably shouldn't because it's not what other people think. But you're getting a look at what's happening in my mind. I'm like, iron, iron, iron. Wow, I never would have came up with that. Okay, which of the following samples has the largest number of ions? Notice we're starting with 1 gram of each. So let's do this just for the beryllium chloride. I've got 1.0 grams of beryllium chloride times 1 mole of beryllium chloride over, and here I look at beryllium and it's 9. Chlorines are 35 and a half roughly. So 2 chlorines is 71. 71 plus 9 is 80. And I'm just going to do that. And then times 3 mole of ions per 1 mole of beryllium chloride. Now, how in the world do I know that? And the answer is, I'm going to put this down here. Beryllium chloride is made out of 1 beryllium and 2 chlorines. The chlorines are -1 because of where they are on the periodic table, and the beryllium must be a +2. So I've got 1, 2, 3 ions for one of these, or 3 mole of ions for 1 mole of that. And that's where that comes from. Any questions about where that comes from? Okay, so I'm going to have some number here, and then I'm going to have 1.0 grams of MgCl2 times 1 mole of MgCl2 over Cl2 is 71 again, and Mg is a 24.3. So 71 plus 24.3 is 95.4 times 3 mole of ions per 1 mole of MgCl2. And if we scroll on down, do you see that we have 1.0 grams of calcium sulfide times 1 mole of calcium sulfide over calcium's 39. Nope, calcium's 40, and that's 32, 72 grams times 2 mole of ions per 1 mole of calcium sulfide. So why is this 2? 1, 2. So if we take a look here just at these first 3 and understand that we're asked which has the largest number of ions, which calculation is going to give us the largest number? So let's look at these first 2. Which is going to give us the larger number, A or B? Well, the calculations look exactly the same number-wise, except this one you're dividing by 95. This one's you're dividing by 80. So this is going to be bigger. Okay, so A is the winner. How about A or C? Well, here, 72 and 80 are different, but they're only off by 10%, right? They're pretty close. But here you got 3 versus 2. When I multiply this sucker by 2 versus this one for 3, this one's going to be smaller. When you look at D and E, this has 2 here, this has 2 here, and the numbers for both of these are bigger down here. So the answer is A. This would be a great question to put on a quiz because you don't really have to do all the work to figure out what the answer is. Any questions here about what the answer is on 118? Are we good to go? Okay, let's go.
Yeah.
Okay. what are the names of BAF, SI4, and NiBr2? First of all, you have to realize that this one is ionic because it's got a metal and a non-metal. Secondly, you have to recognize that this metal is in group 2A, so you don't write the charge with the name. So this is barium fluoride. This one is also ionic because it's got a metal and a non-metal. Secondly, nickel, you have to tell people the charge. And when you know you've got one nickel and two BRs, and you know the BRs are -1s, then you know the nickel is a +2. So the name of this is going to be nickel 2 bromide. Last one here. Whenever you see a metalloid combined with nonmetals, you're going to assume molecular. And that's one of the traits I probably should have put down for metalloids, is that they form covalent bonds. So molecular, we're going to say is silicon, and then tetrachloride. Any questions about those names?
No.
Okay. So we've already answered which of the following are ionic and which are molecular. Ionic, metal, non-metal. Ionic, metal, non-metal. Here, not a metal and a non-metal, so molecular. Which has the larger mass? Well, we got 0.50 mole of BAF2 times barium is 137. Fluorines are 19, so that's 38. 38 plus 137 is 175. So that's going to tell us how many grams we have. 0.50 mole of SiCl4. Chlorines are 35.5 roughly, so 2 are 71, 4 are 142, plus 32 is 174. Wow, those weigh about the same amount. So based on my ish, I'm going to give it to that guy. Now, nickel 2 bromide, bromines are 80. So that's 160. 160 plus 58.7. 160 plus 58.7 is 218.7. So the question is which has the larger mass? Do I actually need to plug the numbers in to see which one is the largest? That's a yes or no. Do I actually have to
No.
plug the numbers in?
No.
This should be enough work. And so I'm going to say this is the largest. Why? Because that's the largest. I mean, this is almost like a duh. Okay. Now, here's another problem like the one we had done before. This is a great problem for you to try on your own, where we take percentages. And remember, you take the percentage, assume that many grams, turn that into moles and get the formula. But I do want to get to this one interesting problem here, because you're going to do a lab similar to this one, only I'm going to change things a little bit. I'm doing a little work over here. I'm going to cross this out, and well, we'll just leave that there. So let me show you what we're talking about here. Is we're talking about this hydrate, which is KAlSO42 dot XH2O. So this is a hydrated compound. It comes with H2O. It's actually a solid. When you heat this, you can actually drive the H2O off. So we would get KAlSO42 plus X H2O. That plus sign means we have separated the H2O from the ionic compound. So now we have the ionic compound without H2O. Now, this is a solid, and this is going to be a gas when we heat it. So we have 4.74 grams of this. And normally when you heat something like this up, this escapes as gas and you don't collect it. But since this is a solid, you have that left over. So normally you'd be given this information, you have 2.58 grams left, okay? And here you would have to figure out how much H2O. So how do we figure that out? Well, 4.74 grams should equal 2.58 grams plus X grams of H2O. I'm going to call this A grams of H2O. So that means that A grams of H2O ends up being 2.16 grams. And that's what they give you here. So normally you don't weigh the water, you figure it out because it gets away. Any questions about this problem so far? So I'm going to go ahead and put 2.16 grams here. So how do we do this problem? Let me show that to you. So I'm going to put this all down here at the bottom. And to do this problem and to figure out what X is, we take our 2.58 grams of KAlSO42 and we multiply by 1 mole of KAlSO42 over however many grams 1 mole is. So just to do this really quickly, I know that this sulfate is 96. So 2 of them is 192. I know aluminum's 27. So I've got 192 plus 27, and I know potassium is 39. So I'm just doing a real quick job on this. That's 11 plus 7 is 18, carry the 1, and that's 5, carry the 1. So we're talking about 258 grams of potassium aluminum sulfate to 1 mole. And we're going to get moles of potassium aluminum sulfate. And then we're going to take that 2.16 grams of H2O, and we're going to multiply by 1 mole of H2O for every 18.02 grams of H2O. That's the molar mass of H2O. And here, I'm going to call that X moles here, and I'm going to call this Y moles of H2O. And then to figure out the ratio here, you just do this, Y mole of H2O over X mole of KAlSO42, and we're going to get the ratio. So let's do this real quick just by estimating. How many times does 258 go into 2.58? And I would say it goes in, if I put my decimal there, it goes in 0.01 time. How many times does 18 go into 2.16? Well, it goes into 21 one time. And that's going to be 0.1. And then left over is 3, 36, and then 2. So the numbers I'm going to use here are 0.12 H2O and 0.01. So we're going to get 12 to 1. So the formula is going to be KAlSO42 SO4 2 12 H2O. So that would be potassium aluminum sulfate dodecahydrate. Oh. All right, Alice, what happened to you? All right, Alice, are you back? So this is how you find the formula of a hydrate. And we're done. Any questions about this last one and why it's 12 to 1? Okay, this is yes or no. Are you alive? Okay, there's a no on Gabe. Gabe's not alive. Shine's, only Alice is alive. Oh, Sadie's alive now. Shine is alive. Gabe, come on, you can do it. Oh, Gabe's not. Gabe, are you alive? Give me a thumbs up. All right. Oh, Gabe has a hand raised. Go ahead, Gabe.
I'm barely alive.
Oh, wait, no, that's not barely alive. It's barely alive. I'm barely alive because I had 2 quarter-pounders last night and I'm still digesting. Okay, I didn't have 2 quarter-pounders last night, but
Hey, Tony,
yeah.
my
Yes.
internet failed and I'm just looking at what you had written down there, and I can cover it myself or go back and watch the video, but where'd the 18 grams come from was just my quick question.
That?
The 18.2, is that?
It's the molar mass of
Yeah.
water.
Okay.
Each oxygen is 16.
Okay.
each
Yeah,
hydrogen 18. These are molar masses.
oh, okay. Yeah,
That's it.
right.
All right, people. Thank you
Okay,
for attending,
thank
and I
you.
appreciate it. And hopefully we'll see you tomorrow. You're going to be doing a lab tomorrow like this one with your calcium sulfate stuff. So you're going to need an oven. It might work in a microwave, but I'm not sure, to be honest with you. So I'd use an oven. Okay. Turn your mics on. Say goodbye to everybody.
Adios.
Bye.
Bye. Thank you.
Sayonara.
Bye, thanks.
Okay. And end meeting.